at this little recipe that we have here for the waffle recipe, or the waffles, right? And so you just had to write a balanced equation with that, although there was no balancing involved. Please don't try to balance it. Nothing matches up, right? So, but what you should have had was you should have had your, sorry. There we go. 3Wm plus 2Eg plus 1Mk yields 12 Was, right? And so basically what we were saying was the waffle mix, the eggs, milk, and waffles, right? So that was what step 1 was telling you to do. Then it asked you how many waffles can be made with 6 eggs. So we probably might have approached this 2 different ways. Let me scooch that up there. So we'll leave that up there. Okay, so how many waffles can be made with 6 eggs? So how many of you guys did that there are 2 eggs for every 12 waffles, so 2 is to 12 as 6 is to something, and you did a proportion. How many of you guys did that?
I just multiplied it.
Cool. You just multiplied because you saw, okay, all right. Did anybody actually go back to kind of what we've been working on where you did 6 eggs, 6 EG, words came down to the right, you went up to waffles, so then you had a 2 to 12. Did anybody do it that way? I guarantee you guys are going to start doing this in your kitchen now. It's going to be great. No? No? Okay. All right. Well, anyways. Huh? Yeah. Not if you have to change your recipe.
But I don't. I don't
Think outside of the box. All right. Okay, let me get you guys through this. So what was the answer to number 1?
36.
36. Good. So we had 36 waffles. Cool. All right. Question number 2 said, how much milk could be used? Oh, I'm sorry. How many cups of waffle mix are needed to make 20 waffles? So we had 20 waffles.
And then I had 3 over 12. I did that.
And then
3 over 12.
waffles. So then we had waffle mix on top. So you had 3 over 12.
12. Yeah.
Okay, what did you guys get for that one? 5. 5 cups of waffle mix. All right, then the next one was how much milk must be used with 5 eggs. So you could have had the 5 eggs. Words came down to the right. You compared it to your milk, or you related it to your milk. So 1 milk for 2 eggs. So 5 times 1 divided by 2 was 2.5 cups of milk. Good. Okay. Okay, so real quick, what is this step related to what we've been doing? That's your mole bridge. That's your mole ratio, right? So all of these were considered what type of problem then? Mole to mole, right? Mole to mole. And that's what our examples are going to look like today. So just remember back to this. Okay. All right. So the next part of this question, we're going to expand and we'll move that down there. Okay. So the next part of the question gave you a specific amount that you have in your house. 18 cups of waffle mix, you have 9 eggs and 5 cups of milk. And you want to try to make as many waffles as you possibly can. So you are going crazy with the waffles, right? So this thing says, okay, well, if you're making them in batches of 12 waffles each, which ingredient ran out first? So what did you guys say?
I put eggs.
How did we figure that out?
It's the least. 18 over 3. Wait, no, wait. Yeah, 18 over 3, 2 over... Wait. 18 over 3, 9 over 2, 5 over 1.
Okay. Did you guys hear that? How many of you guys did it that way? Where you did basically, you took the 18, you divided by 3, you did 9 divided by 2, 5 divided by 1. Which all of these came from the mole ratios across the thing, right? And we were talking about how many batches of waffles could we make, and that kind of told you how to divvy it out, right? So how to distribute that out, okay? So how many of you guys did it that way? Cool. How many of you guys actually like drew yourself a picture of this little recipe and figured out how many you could make and which one would end up good? Okay, so we have our visual people. I just want to kind of point out that we all have different brains. We all think different ways, and that's fine. Okay? How many of you guys went to stoichiometry? Yeah, Miss Vogel did. Okay, all right. So, like I figured out how much each one would make, and that's actually going to be the way that you're going to approach today. But it's still related to what you did. Okay. So the answer was eggs for sure. We'll kind of look at that in just a second. Okay. But question B said, how many can you make? What did you guys come up with for that answer?
48.
It is not 48. It's not 4.
Wait, what's 4.5 times 12? Oh, that would equal 54. Wait.
Okay, so this way you have something to work with today. Okay, I'm just going to show you my work from earlier. Okay, so there's that. It'll be up on the screen in a second. All right. I know I kind of wrote all over it earlier, but this was how I had it. So I set up the little mole ratio, mole to mole thing. I figured out how many waffles each one of those ingredients would make, right? So we have 72, 54, 60. You already saw that I X'd out those two. Why did I X those out, do you think?
Aren't divisible by 12. Wait, never mind.
What he said.
You would need more eggs. Exactly. Is it even possible to make 72 waffles, not changing the recipe or the size of the waffle? No, it is not possible. Okay? Therefore, the only plausible answer is this one, the smallest that it can make, the least amount. Okay? And that's going to be what our big goal is today in our calculations, is that we want to figure out, okay, which ingredient, which reactant is going to run out first, because once it runs out, does the reaction go anymore?
Okay.
Are there enough atoms and molecules to bang into each other to form this new compound anymore? No, okay? So your limiting reactant is one of the most important things that you figure out when you're doing labs or when you're figuring out your little chemical equations, okay? But I want you to come back to this, and every single time you guys forget, I will show you this picture again and say how many were possible. And it was only 54. You cannot make 60. It is not possible. You cannot make 72. Do we got the big idea? Yes? All right. So turn to the limiting reactants notes. And we'll kind of write some stuff there. Okay. So for limiting reactants, okay, the definition of limiting reactant, again, think of the waffle situation, was the ingredient that ran out which stopped production of those waffles. Same thing. For this, your limiting reactant is going to be the reactant that limits the amount of product that can form, that is possible to form. Okay? It's the reactant that gets used up first. Once it is used up, the reaction has to stop. Okay? So, usually you will see me label this as LR, just so you know. And then excess reactant, I've seen some people label it as ER, but me, I usually train you guys to exit out. And that way, once you figure out who your excess reactant is, just put a nice little X. Don't scribble it because I have to see your work, right? But you can put a big X over it so that you don't pay attention to that number anymore. Because basically, once you've eliminated it, it's not going to matter. Okay? All right. So we have that. So these two little steps, I'm not going to follow them. So again, if it's something that you would like to follow, that's up to you. I made a mistake when I made these copies. So I'm just going to kind of do this on mine so that you're not looking at that on my screen. Okay? Okay, and so what we're going to do instead is solve for one product from each reactant. So these types of problems give you more than one number in the problem. That's how you're going to recognize that you have to treat it like a limiting reactant problem. You got to figure out which is the only possible answer, right? If it's not possible, then that's not going to be the answer. All right, so solve for one product from each reactant, meaning do one railroad track or dimensional analysis thing all the way across from each of the reactants, solving. You get to pick whichever product you want. You just got to be comparing the same thing. So once you've solved for that product from each of your reactants, so you have two railroad tracks going across, how are we going to recognize the answer? Which one is going to be your limiting reactant?
The least.
The one that's the least, yeah. Limiting reactant produces the least. Yes.
That makes sense.
It does, right? Just like the waffle thing. So keep that in mind. Okay. Yeah, great. Oh boy. Leave it to y'all. Okay. All right. So, looking at this example again, if you choose to copy what the page is actually telling you to do, that's up to you. I'm not going to do that right now in the notes. So, if you want me to explain it to you later, you can come see me. So, I'm going to scribble that out. So, we're not even looking at that. I'm going to treat this problem fresh. All right. So, let's practice our naming because you guys need to. What is this guy? Silicon dioxide. Good. Who's this? Hydrogen monofluoride. Yeah, I'm hearing that you guys are. Tetrafluoride. Good. Silicon tetrafluoride. And this one? Don't say water.
Double oxide.
Dihydrogen monoxide. All right, cool. Okay. So, if you notice, in this problem, it gives you two different numbers. Do you see that? Do you see how that's different from what we've been doing?
Yes.
Good. All right. You have two different numbers given to you in the problem. That right there is your indicator to know it's a limiting reactant problem. All right. So, with that, we're going to do our step one, which says solve for one of the products using each of the reactants. So, you guys get to pick which product we want to solve for. Do you want to solve for silicon tetrafluoride or water?
Water.
Water. All right, sounds good. That was the one that was shouted out the loudest. All right, so we're going to go 2.0 moles of HF. Okay, we're going to bring words down to the right. This is just a mole-to-mole thing. Could we expand, by the way, and start from grams?
Yeah.
Yes. Okay, did you guys hear the question? Could we expand that and not start at 2 moles of HF, but start at like 2 grams of HF and still get to that mole bridge?
Yeah.
Yes, you guys know how to do that. Good. All right. So we have moles of HF. I'm going to bring that down to the right. Okay. What is this next step going to be? If we're already in Mole Town, it's the mole bridge. Exactly. All right. So what is the number that we're going to put in front of HF? 4. So there's going to be a big 4 down here. What am I going to put on top?
2 moles of hydrogen of dihydrogen
Yes.
monoxide.
Of the water. Good.
Oh, okay.
You're good. That was just a practice. I appreciate it. That's your mole bridge. That's your mole ratio. Okay? So 2 times 2 equals 4. Divided by 4 equals 1. All right. So with this recipe, or with this ingredient, we're able to make 1 mole of water. Do we see that? Think about the waffles again. Because we picked H2O to compare it to. We get to pick one of your products, and that's who we're going to go to. You could have also picked this, but you have to do it for both of them, okay? All right, so let's do the second one. So we also have the 4.5. I'll write that with a different color. Hold on. There we go. All right, so we have 4.5 moles of silicon dioxide. I'm going to start moving through this a little bit quicker. So we would put a what at the bottom? What number would we put at the bottom?
1.
That's going to be a 1. Where is that 1 coming from?
Coefficient.
The fact that there's only 1 of the silicon dioxides, right? So 1 SiO2. I'm being lazy and not putting moles. You should still put moles. And then we're going to go to 2 moles again of H2O. So once again, we have our new, okay? We have to compare the same thing. That's why we didn't change it to be silicon tetrafluoride. Do we see that?
Yeah.
That's one of the biggest mistakes people make. Because you don't want to know with this ingredient how many waffles you can make and this ingredient how many pancakes you can make, right? You need to compare waffles to waffles. All right, so when you guys solve for that, we have 4.5 times 2, so we get 9 moles of H2O. All right, so looking at this, can we answer the question, who's the limiting reactant?
Yes.
Who? HF. Because we made less moles of water using that ingredient, meaning this one is in excess. It is not possible ever.
Wait, I'm so sorry, but the term is if it's an excess.
Excess reactant? Huh? Yeah. Anything that's not a limiting reactant is excess. Yes. Yep. Okay, so let's look at this problem. So it says if we have 0.75 moles of dinitrogen tetrahydride, all right, mixed with 0.5 moles of hydrogen peroxide, okay? Okay, what is the limiting reactant? So, which product do we want to pick this time?
Nitrogen.
Let's do,
H2O.
Nitrogen.
so,
Nitrogen.
H2O. I'm not gonna go any louder. I sounded going.
Are we seriously fighting?
I love that show.
Paloma? Yes, yes, we are. Okay, all right, so let's go ahead and get this started. So we got that of N2H4. Whenever you have a 1, you should go for it. So on the other one, it would have been easier if we had a 1, if we had done the 1. Just heads up. All right, so let's keep going. Bring words down to the right. What's the number that's going down here for a mole bridge? Talking about N2H4. It's a 1. The coefficient is a 1.
She's saying yes.
And we are relating it to 1 mole of N2. Do you see how that's going to make that one so much easier?
Yeah.
Okay. So find any shortcuts that you can. If you have a 2/2, that's awesome too. So look for ones that match the mole ratio so you have to do less math. All right. So 0.75 times 1 divided by 1 is 0.75. On the other hand, our other reactant is 0.5 moles of H2O2. Okay. And we have 2 moles of it in the balanced equation to the 1 mole of N2. So 0.5 times 1 divided by 2 is?
0.25.
Yep, 0.25. All right. So which reactant is our limiting reactant?
Water.
It's not water, but it's hydrogen peroxide. It looks like water.
Oh, okay.
All right. So H2O2. This is the only possible amount that we can make. Okay? All right. And then, so I would X that out so that you don't even pay attention to that whole calculation. But look at the next part. It says how much in excess. So how much didn't react? So that's the other type of question or the addition to this. So let's think about this for a second. So if this is my limiting reactant, that means that's the only number we care about. So when you have this kind of question, you base it off of your limiting reactant. And you're basically gonna stoich it out to where you are figuring out how much reacted with it. So we're gonna have that 0.5 moles of H2O2. Words down to the right. But we're gonna relate it to the other reactant, which was the N2H4. So it's just like problems that you've had in your homework where it says, how much of this is needed to react with 5 moles of this? All right? So it's the same thing that you've been doing. It looks weird, but you're just comparing the two reactants, or you're just relating the two reactants. So this is just going to be a 2-to-1 ratio like that. Okay? Hold on. So when we get this, okay, we have our 0.5 times 1 divided by 2, 0.25 moles of N2H4 were used. Do you see that? So if we've answered how many were used, can we now turn around and answer what we have left over?
Yeah.
Yep, because we would look at how much we started with, which was what? 0.75 we're started with, minus how much were used. What's the answer of how many were left over? 0.5.
I know it's like all the same numbers.
Yeah, I know. That's the only annoying thing about this.